Hey everyone, welcome to my video on the center of mass, actually the first of a couple. And what we're going to do today is just look at these one-dimensional point systems. The next one we'll look at 2D systems, point masses, and composite shapes, and then we'll go on from there to other crazier flat 2D shapes. But for today, we do want to start talking about what's called a moment about a point. So this will help us talk about center of mass defining what's called a moment. And we'll get to this website in a minute. The moment about a point mass, about a fulcrum point, the distance of the point from the fulcrum times the mass or weight of the point. So some key words in there: fulcrum, this is kind of your center. So if you were to draw kind of a picture of what that looks like, you'd have, say, some beam, one-dimensional beam. We're going to put our fulcrum right here. So this point right here is going to be what we call the fulcrum. That's our center, where everything should balance out. If everything is where it needs to be, we're going to place a little mass over here. So this could be say like 10 kilograms or something like that. Sometimes we'll also use maybe just if you have like a stack of pennies or bricks, you could say just 3 pennies or 4 bricks or something like that. So, but just some way of counting how much stuff is there. And then so this is going to be what we call our mass. So there's our mass. And then how far that is from the fulcrum, that is going to be our distance. So this is our distance right here. And what we do to get the moment is we just multiply those two numbers. So how much stuff, the mass times how far away we are from the center, that fulcrum point, that is the distance. And when we multiply those, we get the moment. Now, what the moment tells you is kind of the tendency this has to rotate either up or down around that fulcrum point. So we could imagine if we had a big mass right here, this is going to go down this side. If we put maybe a mass over here that was heavier, then we might expect this side to go up. But it just tells you how much of a tendency there is to rotate about this fulcrum point. So the bigger the moment, the more tendency there is to rotate, and probably the faster it'll rotate. A big mass or a large distance, more tendency to rotate because you get a higher moment. The closer in that mass is, or the smaller the mass is, then you have less tendency. So that's kind of the idea of a moment, is just how much tendency is there to rotate or to drift away from balance. Now we'll go ahead and take a look at this website real quick. And what this allows you to do, click on that first point, is to go ahead and place some objects on this balance beam. So you can say put a few objects on here and remove the support. So those columns are supports right there. And then you can see, I had 15 at a distance 4. So that is going to be a higher moment than this 5 at a distance 5. So it's going to tend to rotate to that side. And you can move these, experiment a little. Now this one's going to have a larger moment on the left side, so it's going to go toward the left. And you can just kind of play around with that and see what you get. If you want to take stuff off, you just drag it back over here. So what we're going to do is go ahead and place a few things and just calculate some moments. So I've done one already, we might do one more. But the idea is kind of fill this chart in and see what's going on for things that balance. So I'm going to put a mass of 10 at -6 and a mass of 15 at 4. So we got 10 at -6, so that's going to be on the left side right there at 6. Mass of 15 at 4. And if you don't want to wait for that, you can just put supports in and then take them away. But it should balance out. And if you calculate the moments, this is going to be -6 times 10, so -60. This is going to be 4 times 15, +60. and you can just record those kind of right there on the chart for those two moments. So those two together are going to be balanced. Now, if you want to pause the video, put in a few more scenarios, you can. Try to come up with some different ways that you could balance on each side. And I'll go ahead and fill in maybe one or two more, just pausing the video as I go and see what we get. So here's one scenario where you have 20 at a distance 2, that gives me a moment 40, 5 at a distance -8, that gives me a negative, that should be 40 right there. And if you want to view what that looks like, here we have it. So 20 at a distance 2, 5 at a distance -8, but moments of 40 on both sides. Now I could also maybe, instead of just putting a 20 at the 2, maybe I could put a 5 at the 4, and maybe a 5 at the 2, and maybe a 5 at the 3. So you can play around with what you think might work, but it should be the same moment on both sides. Maybe a negative on this side and a positive on this side, but the numbers should match up on those. So if we had 20 here, I would probably need another 20 to get that moment. So maybe we could put 10 at 2, and this would balance out. So there's multiple ways to get these. You don't always just have to use 2 bricks or 2 stacks of bricks, one on each side. You can do multiples. The moments will add up together. So this is 20 and another 20, which would give me 40, matches with the negative 40 on that side. So there's a few ways to do that. And if you're still not quite getting that, go ahead and play around with that a little bit. See how you might get a few more of these. I'll go ahead and pause it, fill in the chart, and then we'll go on from there. So what you'll notice is as you fill in the chart, your moments should always follow the same pattern. So if it's balanced. So in this case, the negative 60 and 60, I get a total moment of 0 right there. 40 and negative 40 again, total moment of 0. Negative 40, 20 and 20, total moment of 0. So your total moments should always add up to 0 if you're going to be balanced. And that's going to be a key idea through a lot of what we're going to do. So that's something you could record right there on your observations. So the moments should add up to 0 to be balanced. All right, we'll go ahead and take a look at this one right here. So on the left side of the balance bar, place 2 bricks at distance 2, 1 at 5, 1 at 7, and then find 2 ways to place the bricks on the right side at a single distance so the system balances. And I'll go ahead and pause the video a minute, probably just do one in the video, but pause it, see if you can get a couple ways that might happen. All right, so hopefully you are looking at this kind of idea. Putting 2 bricks at distance 2, calculate that moment, 1 at a distance 5, 1 at distance 7, so that gives me a total of 16 on that in terms of just number of bricks. So we also want a 16 on the other side. So if we go ahead and I've already placed the ones on the right side. If we go and look at how we're going to get 16 on the left, I might could put 4 at 4, I might could put 2 at 8. If I had fractional bricks or fractional units, I might could do some other scenarios, but we'll just go ahead with whole numbers. So I'm just going to put 2 bricks there to distance -8, and that would balance everything out. So that's kind of the idea behind these moments, looking at this guy right here. We'll go ahead and record that one down. So we're going to put 2 bricks at a distance of, let me say, -8. And if you want to do, I'm just going to go ahead and put a unit there. So this is 2 bricks. If you want to put your units in kilograms, you can do that. So this would be 10 kilograms. But the idea is, well, no matter what your units, kilograms, bricks, whatever it might be, that you're going to get the same moment on both sides of that fulcrum. So we said another way we could do was 4 and 4. If you're only using one brick where we need to place it, well, one brick would have to be 16 units to get that mass times distance to multiply to 16. So in theory, if the bar were long enough, this would be at negative 16 for the left. That one would also be a negative 4. So that's kind of the idea there. The last thing that we'll take a look at, and this is looking at the 1D point mass system definitions. So the moment of a system is going to be adding up all the mass times distances, and I'm using this summation notation right here. The total mass, you're just adding up all the masses, and the center of mass is going to be this moment defined by the total mass. So the total moment over the total mass, big M over little m. So that's kind of your idea behind the center of mass. Is I want to find what place can I put my fulcrum where everything's going to balance, where my moments are going to be the same on both sides. And the way that we can do it is basically by doing an average. We're going to add up all our individual moments, add up our total mass, and then we'll just divide that out. So we got one more website we'll take a look at right here and answer a couple questions. So this is my scenario right here. I have a mass of 2 at negative 4. I have a mass of 2 at 2, a mass of 4 at 6. And what this website is going to allow you to do is kind of change the weights or the masses over here. You can drag where they're at by just dragging the top of the point. And this one, we can also drag this fulcrum around. So we'll drag that around in a second. But you can tell there's going to be some different ways that this balances depending on where that fulcrum is. So right now you can tell it's kind of overloaded over here on the right side. There's a lot more mass, especially this B at a further distance. So you got a larger moment, you're going to tend to rotate. But let's go ahead and calculate where this should go to balance out. If we go back here, we're just going to start multiplying these. So the total moments are going to be this 2 times negative 4. So the 2 times negative 4 is going to be a negative 8. 2 times 4 is going to be or 2 times 2 is going to be a 4. And the 6 times 4 is going to be a 24. And I'm just going to add all those up. I should get 20. Add up the masses themselves, no matter where they're at. So 2, 2, and 4 gives me 8. And then just divide that out. And so we're going to go ahead and divide that out and get, let's see, 20 for the total moments over 8 for the total mass. You can go ahead and divide a 4 into each of those. So that's, 5 over 2 or 2.5 on that. So let's go ahead and come over here and check it. So we can put it at 2.5 is where our fulcrum should be. That will balance this system. If I recalculate the mass times the distance away from this new point at 2.5, I should get the same moments on each side. So this, like I said, a way of averaging the moments and dividing by the distances from before gives us this new center of mass point that we have right there. So that's kind of the idea that we want to follow on these guys. So coming back to my worksheet, 2.5 would be about here. And that's where I would say I get my center of mass. In the future, like I said, we'll go ahead and look at 2D. You should go ahead and complete the worksheet and try the homework exercise at the end. This is going to be just calculating where is the center of mass, what are the moments, that sort of thing. So let me know if you got any questions.